All right, folks. Hi, everyone. My name is Alexander, and today I'm presenting one more talk about functional programming. This time in OCaml, free monads in OCaml. But before I start, um, yeah, I would like to know if the connection is okay. Do you actually hear me? I see many people are today here, right? And that's good. Yeah. Hmm. All right. So it seems everything is working. Let me double check the connection and listen it. Hmm. Yeah. Yeah. Seems it working right. So turning it off. Turning it off. All right. Hmm. Interesting. All right. Kakadu is writing, hey, hey Kakadu. Nice to meet you. All right. So how are you doing today? Are you ready to learn something new? Free monads in OCaml. Why did I even decide to present this talk? Well, 2 days ago, I've seen this post by Dmitry Kovanikov. He says he needs free monads in OCaml, and he made a reference to his free monads talk on Haskell. I've watched that talk and decided why waiting for 100 reposts. Dmitry requested 100 reposts. These monads are free. I can give this talk for free, I thought. So this is what I am doing right now. Yesterday I learned OCaml a little bit, and today I'm able to provide you with some interesting info. I hope this will be at least useful. You can certainly ask questions in chat. I'll see it. So let's start from several general questions. What is abstractions? Why do we need abstractions? And what kind of abstractions are there? So I divide abstractions into classes: genericity-like abstractions and interface-like abstractions. And they have a really different usage, and they are quite different in behavior, because genericity like abstractions mostly work on compile time, uh, on the level of types mostly. But this is not the general rule, but it's a good rule of thumb to distinguish them from interface like. And genericity like abstractions such as generics, templates in C++, various type classes and traits, type level bits such as maybe type families from, for example, from Haskell, and other things that work on compile time. They can solve a particular set of tasks that is related to generalizing some algorithms, because genericity like abstractions are mostly about pure uh, properties of some types, whereas interface like abstractions uh, is what we really need in our programs. While genericity like abstractions very useful in libraries, generic ones, while interface like abstractions can be used to separate responsibilities of the application, to denote some subsystems, to abstract from implementation details. And interface like abstractions mostly work at runtime, but yes, they can be defined at compile time, like interfaces from Java, yeah, right? Or abstract classes from C++. They can be defined on the level of types meaning they will do some relation to compile time, but they work at runtime and they have some objects behind interfaces, objects or maybe implementations, and these objects or implementations have lifetimes. They have a specific representation while the program is running, but genericity like abstractions mostly vanish after compilation. They don't really have a representation in runtime. Well, except cases when, very difficult cases, when we make them be presented in runtime. That's mind-blowing. Programming, for example, dependent types or something like that, we will not touch, because this division can be, it's a very clear division, but there are things on the edges of both interface like and generic like abstractions. Because, for example, type classes, they can be interface like, they can serve this purpose, but it will be not very a good interface like abstraction. Haskellers love type classes as interfaces, but I don't think it's a good idea. So going closer to free monads, free monads are interface-like abstractions, and they are very functional because we have OOP-ish abstractions, interfaces from Java and C#, abstract classes from C++, traits, and well, maybe a little bit of type classes too. First class modules in OCaml, but functional programming also has interface-like abstractions, although they are not often seen like this. Barry functions can serve this role, really. It's not a very convenient interface-like abstraction and very limited one in some sense, but they really can do things every sane interface-like abstraction should do. But also interpretable EDSLs are in FP interfaces, and free monads is a specific class of interpretable EDSLs. And why should we use them? Well, no one should, but there are benefits in free monads that will make your application very nice. Functional programming, in functional programming, it's traditionally was a problem to make interface-like abstractions, and people were wondering how to do that. They invented effect systems, so they invented reader T pattern, service handle pattern. I think, well, they invented free monads, but they didn't haven't considered free monads as interfaces, because this topic, like what interface is, wasn't really presented in functional programming discussions some time ago. But I'm really, in my materials, I'm demonstrating that free monads is the most adequate and the most powerful analog of interfaces from Java and C#, but interfaces from Java and C#, they are OOP-ish, from like all object-oriented, while free monads are completely pure and functional. Yes, we can use free monads for designing our applications at large, like we use interfaces in object-oriented languages. We can, for example, define two subsystems, each of which will be represented with some free monadic interface, and then we point to these interfaces from business logic scenarios, and this makes our business logic scenarios pure and detached from implementation details, which helps us to keep business logic much simpler. Well, this is not a new idea, actually. Object-oriented and mainstream developers use this idea since forever. In functional programming, we also can and should do something like that. The question is how, and what tools are better for this or for that. And my point is that free monads are very good in this role, and we will see how to use them and a little bit how to implement them in OCaml. Uh, it's a typical situation when you need uh, an application with two subsystems, with one subsystem, and maybe multiple implementations of that subsystem. This time it's terminal. It can be a console terminal or web UI terminal. It's possible to have a free monadic interface for terminal and even substitute interpreters, meaning implementations, on the fly. This will require some inner workings for sure, but it's possible and can be done. Also, this makes terminal scenarios, or maybe just free monadic scenarios, very testable. First, they are just values and they are pure. Second, you can cast your own interpreter for tests. And this can be even a mocking interpreter. So the code with free monadic approach is more testable than a direct impure code. So code. Dmitry Dorogoy is writing, why not to extend FP languages with real interface? They have, for example, Scala has traits. OCaml has first-class modules which work pretty much like OOP. Well, they have very interesting features, and I'm not quite sure about all those features, but still, they work like interfaces, and people use them like that. But it's not a question why we can't. We can. The question is why it's needed. I think OOP interfaces don't really are not as powerful as our functional interfaces. I mean, free monads. So if you have free monads and some support for monads as well, functional interfaces are superb. That's a short answer, but a long answer. It's depends. Historic reasons of languages evolution are very tricky because all languages are different. They're different in philosophy, in internal behavior, and in purpose, and etc. So it's a tough question and should be addressed to every certain language. But let me switch to the code and we'll see a little bit of something. In here, I have some OCaml program that doesn't do anything so tricky. I'm not sure why it's... Maybe this will be a bit better line up. So it doesn't do anything tricky. It prints hello world, then takes several strings organized into list, then uses functional tools to quote each string here, and then prints all the results. And you see it right to the right. So it prints the hello world and strings that are being quoted. This is a usual way to program in OCaml, in other languages. This code is impure, direct. Those functions work with console directly, so you can't really test this code because it's not pure. Maybe there are certainly some tricks, but conceptually you can't test this code. You need to separate impure things from pure, and then test those pure things in isolation. What we can do with that? Well, nothing that much, because this code is hopeless, but we can try to imagine how to program in a different way. Let's think that our programs can be actually not just instructions but values, interpretable languages. Here we are trying to there is an idea that we are trying to come closer, the idea of free monads. Free monads are interpretable languages, and we will see how to get them. So let's try to imagine how to make our programs more pure. They can be, for example, pure values. This is a simple program, and its idea that I can have a list of separate instructions. For example, print and get line from person from the user. And once I get this line, I run the internals of this function. This is a continuation. It's a function that accepts one argument line that comes from here, and then another list of instructions. This time you type it something. This is a very simple program composed from lists, this list and this list, specific values that denote some operations, print, get line. Those are not commands like print string or something, because they don't do anything yet. These are just values. And the whole simple program is a value, it's a list of terminal. Terminal F, we will be call it algebra, we can call it EDSL, we can call it language. It's a language of those instructions. Composing them means composing some program. Let's take a look at this terminal F and what is this. It's actually a simple algebraic data type in OCaml. It has, for now at least, two options, get line and print. And as we seen before, print something. So here we have a field of string. We can put some string into this value. It will be print with some value. Or it can ask the user, that's the idea of getLine, and can continue evaluation with the internal script. This is a function, right? A function that takes what was typed by the user and proceeds with the list of other commands. And this is a recursive type for sure, because we can nest terminal into getLine, and in here we also can do a list of the same functions and etc, etc, etc. So this can be even put into here, and you can do this nesting infinitely. The list will grow and grow and grow. Well, actually there are several problems with such an approach, because the type of this simple program will grow. The more you nest those instructions, the more will have to grow this type, and this won't be convenient actually. Well, maybe I'm not, maybe I'm wrong about this simple program. It won't grow, right? Yeah, this one won't grow. Let's just put another instruction here. Oh, yeah, must be okay. Let's try to remove this and remove this for now and try to execute. Certainly nothing happens because nothing calls this program. I can call this program by interpreting it, and the interpreter will traverse those lists and connect this mnemonic encoded operations to real actions and do the rest of stuff. I can uncomment the interpreter itself. It's actually not a difficult one. It's a function that has one argument. It's not in here, but OCaml, it's an OCaml convention to some functions. It says that it's function that has one argument, and this argument should be matched against those patterns. So once we pass a list to this program, it will be traversed. If it's empty list, nothing will happen. If it's a list with item get line on the first position and something on the rest position, it first needs to evaluate a real action for get line. At this time, I don't have an action for asking me for a string because it's a online compiler. I'm not sure how it will work with asking me for a string. Maybe it can, but I decided to mimic a user. Like a user typed this string. I imagined that. And this string should be passed into the this is called continuation. We've seen it. It's a function that continues what the getLine procedure. So we need to fill this continuation with user input, with the results. It expects results here. All right, and run the rest script here, and it will be run. Then also there is a rest of the script here, so we should run it too. The same things happens for print. This time we can easily print what this print asks us for printing, and then also we need to traverse the rest of the list. That's a very little interpreter, and here it is, it works. So now we have two nested lists, right? Even three nested lists. Well, this will work. We can stop here and enjoy this cool functional programming with pure values because our program is pure and nothing bad will happen. Well, actually, the interpreter may do bad things for sure, and interpreters should be written carefully, for example, catching exceptions or something like that. But in general, our program is pure and lacks implementation details that may occur here in the interpreter. We can enjoy this, but I'm sure you're not very happy with this syntax, right? Yes, this syntax is a bit wordy. Actually, we can do much better. But before we do that, I'll show you another version of the same interpretable language that is done with generalized algebraic data types. It was just made with simple algebraic data types. We can do the same with generalized algebraic data types, and nothing much change, nothing that almost the same, except maybe the syntax. Yeah, the syntax of this algebraic data type tells us that we can also define those options, but in here we see the fields in a more Haskell style, because the fields can be separated with those symbols, arrows, while in OCaml the fields should be separated. Well, there should be pairs, like something, right? But in here we can use some Haskell style, and the final piece of each method is the same terminal. Now it's parameterized, but in here we can explicitly mandate exact return types of a specific method, of a specific action. In this time, I don't request specific types of the terminal. I parameterize this terminal f by unit types. They are just parentheses, nothing else. There's a unit type here is, and the language itself is too weak to demonstrate the power of JDTs here, but it's possible. And when designing more complicated languages, we might want to have JDTs instead and use this mechanism of specifying each type for each method to provide some type safety, additional extra type safety for our languages. This time our language is too weak and too tiny. It doesn't do much, but it works pretty much the same. Yes, we parameterized the type this time and did this with purpose. Otherwise, it's completely the same. All right, still we're programming with lists, which is not very convenient. The teacher in the chat sends us hi. So what's the problem with this program? It's not convenient. We can do better. So let's forget about JDTs. And finally, take a look at some free monads, because free monads, they actually grow naturally is what we've just seen. Do you see? There is a terminal f, this time it's module, but let's consider it's a type that contains the same two options. And this time the t type is parameterized too, like in generalized algebraic data types. And also we see some continuation here, and we see continuation here too. And this looks very close to what we've seen, right? To what we've seen in JDTs, like in here. I can even copy paste and show the similarities. So we did almost the same. There is some method and continuation that will continue the execution, and some return type. Here it is. Just generalize it to unknown types up front, but also print has continuation here. It has a field of string and a continuation. It's a pair, right? And this is a requirement for free monads. We need to put continuation into each method. We could do this here as well, but prefer to not to. Don't mind other business. Just what this gives us. Well, using this kind of structure for our language, we can feed it to the free monads and get a monadic language for free. One comment in the chat, there is a typo in the comment JDT. Yeah, probably. Got JDT. Yes, sure. Thanks. Generalized algebraic data type. The teacher might help people trying to Google the term. Yeah, thanks. So what does it buy for us? Well, I implemented free monad using two resources that you can see here. You can browse that code and that article for yourself and take a look at free monads. Let give me first allow me to demonstrate you not the free monads itself, but the script we'll be writing. I'll uncomment everything and we will talk about the scripts, because we are very interested in usage. 1 second, please. Mm. Interpreters, programs, and runners. All right. So the program right now will be look like following. Program uses this terminal free monadic language, and we can do print line, we can do get line, we can do print line. You see some bindings here, bind. This is a free monadic code. I will understand if you say it's much worse than lists, but it does the same, but it's much worse. Let me run. Hello world, some input from user. Indeed, Sorin Sitsu is writing, could you pass the links, please? Thank you. Into the chat. It's difficult, but yes, probably. Let me open the streamer. Here it is. Let me double check the chat. Not sure they worked. Let me repost them again. First one. Second one. I'll put them into the description of this video. Also, there are in the presentation. I need to share the presentation too. So, all right, let's return to the programs and discussions about 404, right? Let me try to. Yeah. Oh. Works. Two later links work. So let's return to the discussion about free monadic programs. Well, this code is not very convenient. It's still a pure value. It still can be interpreted, but those binds, monadic binds, those lambdas here, they really make the code very cryptic. I'm still learning OCaml, and I don't know whether it has the do notation or for comprehension like in Haskell and Scala. This code could be much cleaner with do notation and for comprehension, but we still can make it much cleaner using combinators. I don't have combinators here, but we can implement them right on the fly. So there is a combinator that looks like this. It's a bind. Bind means take one monadic function, evaluate it somehow, or maybe get some result from it, and pass this result into the another monadic function. So a bind merges two monadic functions into a bigger monadic function. And this time we can get something from println, but actually we are not interested in what println returns. It returns unit. Unit is not an interesting value, so we skip it. Next, we need to bind getLine to the another monadic function. Bind. What do I bind? Let's remove this bind. It will be a little bit cleaner. Let me double check if it works, because I can make a mistake. It works. All right. And let's remove, I don't know, maybe OCaml has eta reduction? Maybe not. All right. Maybe I just missed. Maybe like this. Yes, this works. So println takes an argument, while getLine provides this argument. Both are monadic functions, and when a getLine is evaluated, this bind function takes its result and passes a pure result into println. GetLine returns a monadic result. Bind unpacks it and passes into this next function. So this looks a little bit more convenient, right? I also can reduce it to some degree because this empty lambda is not interesting to us and we actually don't need it. We actually don't need it. We actually really don't need it because this construction returns what we really want. Yeah. So also, I probably can reduce even this code to even more smaller code because empty lambdas are not interesting to us. We just can drop the result with another monadic binding, with another monadic chaining, like this. Yes, it works. So you've seen how I converted some monadic code. We don't yet know how it works. We don't yet know how it's constructed, but I converted it to a pure functional chaining of monadic functions. And this becomes much, much simpler, and this becomes much more pleasant than programming with lists like here. It's the same program, right? Let me copy paste and demonstrate you the differences. It's the same program. Still, this one looks more pleasant and it's quite understandable. It's quite readable. Yes, sure, you can you need to understand what means monadic functions, what means they return values, what means combining them, but you can chain more and more monadic functions into a scenario and it won't be like this. It's a matter of I'm not sure, habit to appreciate this style. After you learned how monadic code works, every monad will work like that. There are many monads out there, so you can bind monadic chains with the same operators and work with all the monads the same way. They look the same, but they do different things behind the scenes. In this time, we do some chaining here and here, those two monadic binds. We put one monadic function inside another monadic function because we still have continuations. And this is what free monads do. They allow us to chain some monadic scenarios. Let me read the chat. Kakadu says let star bind in. Not sure I understood your comment. The teacher writes the equivalent of do notation in OCaml is let star. Oh, right. That's nice. I'll take a look. Let star print and line hello in what? All right. There is a notation for that. Yeah, as I said, I learned OCaml yesterday. I don't feel it on the tips on my finger yet, and it's a lot to learn. Still, I'm able to work with that using my Haskell knowledge. So this is what we do, but how we do that? That's not the only benefit of being monadic with free monads. I'll show you even more interesting tricks. For example, there is a mapm function, and there is a replicate function, and like this, and many more functions to work with arbitrary monads, including free monadic languages. But let's talk about free monads. So we started with this algebra, with this tiny language. Yes, that's a requirement from free monad, to have some continuation that will continue with the nested free monadic code. This one is not free monadic, but this one will be. And let me show you the picture. So what we do, we actually nest free monadic bits. This time it's a roll method, and our language bits, this time it's getLine. Then we nest another free monadic call from free monad, and our call, and so on, so on, so on. The last call in this chain will be a free monadic pure. So roll and pure all belong to the free monad, and those all belong to our algebra. We need several bits to implement that. This tricky nesting. We need an algebra terminal f. It will be a parameterized type. This will be an alias of free monad. It's actually the type. Well, in terms of OCaml, it can be seen as a module or interface. This will be the name of our language, the program, its actual program. It contains the whole script. And there are two bits from the free monadic world. It's the free type, a recursive type. This one recursive too, but this is recursive in a more crazy way, I would say. And a functor not in the terms of OCaml, but in the terms of Haskell. But don't be afraid of the name, because actually the idea of this structure is very simple, and we don't really need to learn the internals of these things, because well, first, it's not that important. Second, there are various free monads, but we'll take a look. So first of all, this is a structure that belongs to the free monad type itself. It's a parameterized structure. It's a parameterized algebraic data type. It has two options: pure, that terminates the chain of monadic functions, and roll, that nests your method, like this, and free monadic method, like those two, parameterized with your method. So it nests itself and your algebra too. Your algebra comes with this t variable. And this is not an easy type, actually, because actually it represents a fixed point, if I'm not mistaken, from abstract algebra, from other mathematical things. I don't really I'm not able to explain how it works, but I was able to re-implement free monads in C++, and this time in OCaml with the help of those resources, without much understanding of the internal this recursive nesting. And functor, all right. In simple words, if you have some data structure, for example, list of integers, it's a functor because we can apply some function to it. For example, function int to string. We can apply this function to this list, to each item in this list, and we will get another list of the same length. That's important. 1, 2, 3, and 6. We will get the same, the list of the same length with changed contents, meaning the type of the contents may change. We can certainly apply int to int, and the type of the contents won't change. maybe only numbers will change, but still it's possible to change the type of the contents, but not the structure of the list itself. It will be a list of 4. So this is what the fmap does. It applies some function to some generic data structures and alters every item in it without changing the whole structure. If it's a tree, it will be the same tree except it will contain different values. If it's a graph, it will be the same graph except maybe it will contain different data assigned to each node, and etc. This is the very high level idea of functor. In our case, it's a requirement of the free monad, because free monads, the mechanism of binding, we can see it here. It's very mind-blowing, but in general, it requires functor to traverse our lists like those one, not lists but scenarios, to traverse them with fmap, and to replace the internal pure with another list, with another monadic script, sorry, to merge two monadic scripts. So the two monadic scripts are like this, and merging them means taking one and putting everything from the second into this pure. There will be only one pure terminator at the end, and the script will be longer. So this is what both free monad and functor do. That's only thing they do. They nest two recursive scripts. Everything else follows from how we use them. Let's keep this aside for a while and talk about interpreters. Naturally, interpreters is where some power comes in terms of evaluation of those scripts. They are interpretable languages, and evaluating them means doing real actions, traversing them bit by bit and doing some actions. Traversing this particular free monad is not difficult. I need to unroll it. Run terminal gets this monadic chain, and the first layer is free monadic pure or roll. If it's pure, this means the scenario is terminated. We just return a specific value stored in pure. It will be the return value of the whole script, but it might happen that the script is much longer, so we need to unroll the next level of this internal script, and then this f is our algebra, or maybe our language. We do the same. We connect each method to some specific actions. Once we did it, we again have a continuation that is nested, right? We pass the results we got here to that continuation. It expects, like previously, like in our simple languages, it expects some results from our upper function, and then continues again with the rest of the chains. So we unroll our free monadic scripts layer by layer. First it's free monad, then it algebra, then again free monad, then again algebra, until we meet pure. That's it. You can create many various interpreters for your purposes, and they can do many mind-blowing things. What else is interesting is that on the level of program, we can make things even more crazier. We can use generic monadic functions. For example, let me execute again. All right, it's just this, but I can, for example, call for replicate m 3 times this monadic function. For example, like that. Voila, 3 times. It's just a value. It's a monadic value, but I can replicate it. I can do even more interesting things. For example, Let's take a look at this code, program 2. Oh, sorry, program 2. For example, I can map some monadic methods over some values. Let's probably, can we rewrite it for easier comprehension? Maybe we can, but maybe we can't. Well, it seems this one is reduced to the most extent. So there is a mapm function that takes another function which does something with each value. This time it quotes each value and prints. And we pass this list to this mapm along with this monadic function. It will traverse everything and will apply an effect. We can call it applying effect. This is an effect. Effect in terms of our language. And what will happen? You will see those functions quoted. Well, we can make it even more obvious, for example, like this. Let me call them because they're commented out. So yeah, voila, we did some mapping. This very much looks like a functor. Actually, it is a functor. What I told you here. So we took some function, we took some list. It will go here, and we got an altered list with altered internals. The same does mapm, but it does for monadic functions. So it's really possible to construct a lot of useful functions that will work with your monadic scenarios, and constructing programs becomes a little bit more powerful because you can forget about loops. You can forget about I'm not sure, maybe impurity, and do some real functional programming here. And this is where the whole power of free monads come. First, it comes from the notions of interpretable languages. From the language that you can, from the programs you can treat as values. And second, it comes from the idea of interpreting. And this is what free monads actually do. If you are interested how they do that, oh well, welcome to learn this code. Actually, this specific code for free monad, like it's a operation that nests your method and again nests itself. It's a little bit mind-blowing. I just copy-pasted it from another sources, but it's actually possible to recreate the same thing in other languages. So if in your imperative language that supports lambdas and probably supports infix operators, you can implement free monadic languages and do particularly the same programming like here. That's probably it. Well, several more slides. This is how the mechanisms look like in the notation I invented for my for my book about types. It's a bit messy here, but there are algebraic data types, there are another algebraic data types with methods, and there are more algebraic data types, etc. Yes, in OCaml these can be modules, but this is not that important. Well, more links to read and learn about free monads. I have a whole chapter dedicated to how free monads work, but actually this whole book it's not about free monads. It uses free monads as a central architectural pattern. It's about a lot of things, but it uses free monads as a central architectural design pattern. So you might be interested in learning it. It's in Haskell, but still can be applied to all the languages, as I demonstrated it here. That's it. That's it. What about performance? Asks Kakadu. That's a correct and needed question, because nesting itself is not free. Nesting means you get one chain, traverse it to the end, and put another chain at the end. Now you have even bigger chain, right? And to nest even more monadic functions, you need to traverse a new bigger chain completely. This is the limitation of this specific free monad. This free monad is called normal free monad, normally encoded. So it's a very primitive free monad. But actually, there are many more free monads that don't have this problem. Yes, of course, there will be some overhead compared to the direct code. Yes, of course, because it's in direction, right? You still need to do some pattern matching over the internals. It's like using pointers in C++. Pointers are quite fast in C++, but it's not that fast as using direct values. Looks similar, but in functional languages it's a bit heavier than just using pointers. Still, yes, this kind of free monad is not very efficient. The short encoded free monad is much more efficient, and I use it. And there is one more no remorse free monad that is implemented in PureScript. If I'm not mistaken, it differs from short encoded. I implemented short encoded and this one normal in C++ and compared them. And also I implemented both in not I implemented but used church encoded and normal from Haskell packages by Edward Kmet and compared them. Church encoded is much faster, but for sure it's not as efficient as direct code. Still, it's very close. Kakadu is writing, in some sense, this looks like inventing interpreted language inside compiled one. Yes, probably, because interpreted languages do something similar, except they need a lot of internal works for the interpreter to parse the syntax and to do stuff. With free monads, you can actually invent a lot of different syntax. I did this for my well, game, not game, yes, game, interactive fiction game. I was tasked myself to invent some convenient way of defining game data for interactive fiction games, and this helped me to find interesting design solutions. Zork-like, I'm not sure how you familiar with that. Interesting design solutions in terms of how it looks like. It looks like this. You can do almost the same in OCaml. This is a free monadic code actually, and nothing extra happens here. It's all the same nesting, all the same chaining, except I redefined several operators. I provided additional monadic functions that work with my notions in the same language, and this started looking like some mnemonic code. This means, for example, we are at the west of house, we get some input from the user, and then we pattern match on this result from the user and move into another location, for example, or do nothing if nothing matched. So free monads open a door for inventing your own syntax. You don't need to parse that, because these are not specific to Haskell, something syntax specific to Haskell. It's just regular functions. They are operators, but regular functions. So you can invent a lot of various syntax for your mnemonic domain scenarios. Dmitry says, what needs to be done to allow commands, program text in our DSL, to be loaded from an external file? Yes, this is an interesting question, and it touches a very deep question of how to parse such scripts. Naturally, it's not supposed that you will be parsing some scripts from an external sources. You will need some extra machinery that will have some extra definitions for the stored languages, and they won't be free monadic, I guess. They will be, well, some instructions in some file in custom format, and then when parsing you can construct free monadic chains from it. But parsing itself will be, you need to write parsing itself. You cannot parse those things directly into your language, at least without much programming of parsers. It's possible, but it's not easy. Well, that's it, folks. Let me know what do you think about it. Uh, is it okay? Do you like it, or maybe you would you will choose something else? Mm, maybe I'll be doing such talks presentations in the future because it's fun. It requires a little bit of preparation because, yeah, I had 2 days to prepare this talk, but still. But maybe why not? Come to here, come to discuss, and that's it. Thank you all, and have a good time. Bye. Thank you. Very interesting, says Sorin C2. Yeah, welcome.